Good morning, everyone. Welcome to class 847. Um, Now, today, I'm going to talk about the entropy cost function. Even though we have discussed about this subject a little bit in the previous class, I want to complete the class today. You may remember that, let's assume this is the deep neural network. If there is an input, it will have output. There will be hidden layers. Once we input vector, we will obtain the output. That is we call for the propagation. And then we will compare this output y with labeled data, that is the target value. We can define cost function. With the given cost function, we can update weight matrix and the bias matrix, and that is called backward propagation. So we will continue repetition of this training process until we meet the target errors. Once y and y dash is less than certain value, we can finish the training. Of course, when we are doing this goals, we always think about the cost. Cost means the time and computing power. Efficiency. So in order to develop very good DNN model, we have to consider this time, computing power, and efficiency. So the reason I'm talking about the entropy cost function today is that, of course, a selection of cost function will affect significantly about the efficiency of training. So during your design of your deep neural network, it is very important process to determine the cost function. And even though we have discussed many times using the mean square error cost function, today I'm going to more deeply about the entropy cost function. Mathematically, entropy function can be described by this equation. Y dash is the target, and y is d and n out. So today we will look at this entropy cost function more deeply and intensively. First, let's take a look at this function. Let's assume that if y is equal to 1, y dash is equal to 1, that means our target value is 1. That means in the classification case, let's assume this x is the input picture and y is the classification. Let's assume that we have a picture here. Probably labeled target output could be cat. In those cases, cat would have been number 1. Then c is becoming minus y dash log y. So then this term is going to be a dominant term to determine the cost. If y dash equal to 0, then cost function becomes So this second term is controlling dominant term to determine this cost. So in a sense, this entropy cost function is a balanced cost function when y dot is equal to 1, and the other case is y dot is equal to 0. So these two different cases, and in both cases, C1 will be minimum value. That is the purpose of our cost function. Let me talk a little bit more about that. This is the definition of entropy cost function. So as I mentioned before, when y dash is equal to 1, then this term is, I would say, a term is becoming this graph. And this second part is what when y dash equal to 0, that this term is coming from the second part. And this graph is corresponding to this B. Let's take a look at closely about this graph A. So as I mentioned before, y dash is equal to 1. That means that this is the target value. So optimal point, this is the where cost function is becoming 0. This is our target. So we will repeat this training process, forward propagation and backward propagation, and we will repeatedly update weight and bias. That is the unknown black box parameters inside this DNN. The machine learning is basically what it's saying is that machine learning, this is becoming a black box. That means we don't care what this meaning of this value W and B. But with the given data and the labeled output, we just keep training until we found the optimal value W and B. As I said before, this is a kind of black box. So we don't want to interpret W and B. We just keep this training process that is coming from computing power. So this is the actual our target where cost is becoming to 0. What does that mean is that we will continue this operation. This is the back propagation. We just keep continuing this training process until this curve is coming from here until this term is becoming to 0. And this amount of this progress will be determined by alpha learning rate. And this when we are changing, updating this y until we get to this point, we use this iteration function. Meanwhile, this point is where y is equal to 0. So this part, initially it will start from here and continuously it will come down to this value. So depending whether your output is 0 or 1, this curve will represent this cost function. If your right answer is 1, but if y is not close to 1, if that is far away from y, if that is near the zero, the cost function is really becoming infinite. On the other hand, if your output is y dash is equal to 0, on the other hand, this target value, but if your output is 1, cost is really high. Eventually, it has to go to this path. This is the mathematical interpretation of the cost function, cross entropy cost function. Let's move up a little bit more about the meaning of this optimization. Let's assume that we have an sigmoid activation function. But however, your output, let's assume that this is y dash, this is target output, and if your output has this kind of shape, and this W and B can change, then in this case, in this area is a little bit difficult mathematics. In this area is where y is really y dash is near, becoming near 0. So this difference is corresponding to cost function, the difference between them, that will be represented in this curve. But if we keep training of this deep neural network, actually this curve will move to this, and eventually it will reach to, let's assume this is number 1, this curve is number 2, and this number is number 3, this number 1. Eventually it will start cost function, it will start here, and it will reach up to 0.2, 0.3, and eventually it will go to 0.4. In this case, I assume that activation function, output function is sigmoid function. Sigmoid function has this kind of shape, and I assume that our target value is y dash. So we have to keep training the deep neural network. How to do that? We keep pushing this output curve until we match the y dash. That is corresponding in this cost function, and we just keep changing. Here is the in the sigmoid function b. If you change b, it moves up to this point. So that means if you update b using the gradient descent method, B1 and B2 and B3 and B4, eventually it will reach a point where C is equal to 0. Now, in this moment of the class, I would like to try to give you all the picture of forward propagation and backward propagation in a case where in the perceptron you have activation function of sigmoid and you have cost function of entropy. So here I'm talking about case B training. I'm trying to find B optimal until when C is becoming to 0. In sigmoid output function, our target is this number 4, where y number 4, and then let's assume that your output is number one curve, then you just keep updating bias B until you match your output Y is becoming to Y dash. That is because dominant area is where dash is near zero. So dominant cost comes from this area, and that function is related to this function. So this action, I would say this is a fitting process, or sometimes I would say this is the regression process, and I'm trying to explain the regression process. So by changing B, cost will come down to this value where C is equal to 1. The reason this entropy part is more dominant is because cost area, most of the cost area is between this Y and Y dash, where this area where Y dash is equal to 0. Let me continue. Let's assume that this is the Y dash curve. And in other case, let's assume that this is Y, and you update B until this point, where this point is where Y equal Y dash and C equal to 0. But in this case, dominant area of cost, this cost is more likely determined by minus log Y, where Y dash is equal to 1. Because this area is more likely Y dash is equal to 1, because this is Y dash curve. So that means that in the cost function, let's assume this curve is number 1, this curve is number 3, 2, number 3, number 4. Eventually, this point is number 1, this point is number 2, this point number 3, and this point number 4. This is cost function. So if you are using the entropy cost function, if during the training process, you will update bias B up to a point B optimal point. That means in terms of cost, initially it will become infinite, but eventually it comes down to a point where Y is Y dash, and that is equal to 1. Why I'm focusing on Y is equal to 1? Because dominant area which determine the cost will occur this area where Y dash is equal to 1. So this is a short introduction, a short explanation about the relationship between backpropagation and forward propagation and cost function, and how our deep neural network is performing the training process, and eventually the parameters W and B will go to W optimal point and B optimal point. So with respect to the activation function, it will keep changing bias until when your sigmoid function, target sigmoid function, and your output function is matched. And the area between the target Y and your output is actually a cost. So eventually you will keep training to optimize B until your target cost function, the cost function is becoming to 0. That is the mathematical description of the training process in deep neural network. When your target is number 4 but your input is number 1, this area, dominant cost area, is the area where Y dash is equal to 0, because Y is here, target output is becoming 0. Then this curve in the entropy function is more dominant. So the cost will be determined majorly by this graph. On the other hand, if your output is on the right side, even meanwhile your target is here, this area is actually cost. You keep changing B until your cost is becoming to 1. The reason is because in this case, most of the area that will determine the cost function is an area where between y is dash is equal to 1 and the difference between your output. That is the controlling this uh, cost function, entropy function. So this 1, 2, 3, 4 means that you keep training until you reach your point to number 4. Number 4 means your output and your target output is equal to 1 both. That is a brief introduction of entropy cost function and training process. Let's talk a little bit more about that. Let's assume this is target output. However, your let's assume this your output. Then there are some differences. This will be the cost. So the slope of this your sigmoid function will be determined by W because the sigmoid function has this kind of shape. So you will keep update W up to a point. So during the forward propagation and backward propagation, you will keep update until cost is becoming to 0. So in the previous slide, I was showing you on case where B optimization. B optimization means the DNN training. But also, we also have to do the W optimization. That is called training. In the cost function graph, so as I mentioned before, our target sigmoid function will be like that. That is y dash. But actually output will be a little bit different. So we will keep changing W up to a point where our Y is matched to Y3. Then initially, we will start with W1 and W2, and it will reach W3. Actually, so we will keep updating that. But this curve actually is coming from the area between Y dash is equal to 1 and our output curve. Because here is the output is y dash is equal to 1, that is curve which is dominant from entropy cross entropy function. Meanwhile, this area will determine this curve. So during the training process, it will have this kind of number and eventually it will reach a point. So sum of these two curves is becoming some minimal point that will become W optimal. It is a little bit difficult to explain this process, but we need to understand the mathematics and also optimization process. But this part is the really essential part of the DNA training process. So we should be able to understand the cost function, and also we should be able to understand the activation function, and also we have to understand forward propagation and backward propagation. I'm trying to explain that process for the case of entropy cross entropy cost function. Now, even though this is a little bit difficult class, let's move on a little bit more. This will be very useful cost function for many cases, such as later on in April, I'm going to talk about the deep neural network models such as DNN and RNN. And many times we're going to use this cross entropy cost function. And I'm going to, this lecture will be very useful when I'm going to talk about those advanced models. So in order to use this cost function, we have to be able to obtain gradient. Because during the training process, we have to update these values. When we update W and B, we have to be able to have gradient. So in order to obtain the gradient, we have to be able to have a differentiation is necessary. Let's do that. So I would like to spend a little bit about the property of this gradient of the entropy cost function. This is the entropy cost function. Using the gradient, we can update W and B until this optimal point. Doing the gradient of this cost function with respect to the weight, we will obtain this term. The first term is coming from the differentiation of this first part. Differentiation of log y is becoming 1 over y. This term is coming from that. And also we're gonna have we will obtain the derivative of the second term and we will obtain this. And also because of partial derivative, we have to differentiate y with respect to w. Because this y is a sigmoid function, we can do the differentiation as we repeatedly did in the previous class. We will have this form. Finally, we can with this term combine this term, because derivative of y with respect to w is actually is y 1 minus yx. By using very simple procedures, eventually we will obtain this form. Then means is that gradient of cost function with respect to W, that is actually slope. You know that update function. So if this term is proportional to y dash minus y, that means that if you have large difference, let's assume that if y dash is large, slope will be large. That is good signal, because if your output and target value has large difference, you will have large gradient. That means your optimization process will be very fast. So this slope of this gradient descent is proportional to the difference between to the target value and your output. That is very good property of entropy cross entropy cost function. It is good property for fast training. At the beginning of my class today, I mentioned that choice of this cost function will affect the efficiency, especially time and cost of your training process. So one of the requirements of your cost function is that you have to complete your training as fast as possible with minimal error. So here you can see that this gradient slope is determining the training speed. So if training speed is fast, then you will have less training time. And surprisingly, if we choose cross entropy cost function, we found that that is proportional. I mean, your gradient and the training speed is proportional to the difference between your target value and y. If you choose mean square error, that is not a case. That is the big advantage of this cross entropy cost function. Let's think about mean square error. For a minute, let's talk about the mean square error cost function. You remember that is cost function was represented by this form. Very simple, easy to understand, square of the difference. But however, you remember that the cost function using cross entropy function is mathematically a little bit difficult, not easy to understand for conventional people. Probably engineers with good mathematical background can get an idea easily, but it is not that easy for many people. But however, mean square cost function, it is easy. Meaning seems to be very easy. But however, you remember that if we combine this with the sigmoid activation function, you remember that update function was delta H and delta was in the previous class, we obtained this equation. So this part, delta is controlling the gradient of this cost function. But you see that delta is nearly becoming 0 when y is equal to 0. And also delta is nearly becoming to 0 when y is equal to 1. In sigmoid function, let's assume that this is our y dash And if this is Y, we have to update W. We have to W update until Y is becoming 2Y dash. But please look at that. In this area, when Y dash is becoming 2, this area really, and this area is really becoming 2, 0. So this area Y is becoming 2, 0, and this area Y is becoming 1. In those areas, gradient is becoming 0. At these corners, this gradient is becoming to 0. That means this part will have very little bit effect to the gradient. So let's assume that you have some difference between your Y target value and Y near when Y dash is becoming 1. That is the case, some case of classification. Then your training will be very, very slow. When your target value is near 0, in this area, the training will be very, very slow because the gradient is becoming to 0. On the other hand, if you are using the cross entropy function, we do not have this term. It's simply becoming the difference. So still, it will update the weight until it reaches an optimal point. Why is that? Because when Y dash is near 0, it has large slope gradient. Derivative of gradient really becomes very high in number. Here also gradient is very really high. So that is the kind of logarithm power. That is a little bit disadvantages of cost function. So especially, let's assume that this is the deep neural network, and if let's assume that number of hidden layer is becoming more than 200, that is, we call it deep learning. This mean square error may not work, because small difference in this area and that area will not change any gradient. Even though you keep training for the propagation and backward propagations, the effect of your W update or optimization effect will be really small. But however, if you choose the cost gradient, the cross entropy function, it will still keep optimization. So that is why sometimes if the neural network cross entropy is more efficient cost function than mean square error. This kind of problem, when Y dash is equal to 1 or Y dash is equal to 0, there will be little bit of gradient. That problem is called vanishing problem. Let me continue discussions on the cost function, especially with respect to a cross entropy function. Let's talk about some numerical example. Let's consider case A, where Y dash is equal to 1. Let's assume this case, your target output is equal to 1, but your DNN output is 0.98. They are very close to each other. I think the DNN is near the end of the training process. then C is becoming, sorry, because y dash is equal to 1, the second term is actually becoming 0. So we consider only the first term. And let's consider a second case. Then again, the second term vanishes and we only consider first term. It becomes case A. So in summary, I would say case A, y dash minus y is equal to and cost function is case 2. Difference was cost was let me explain. Now this is our cost function, and let's consider two different cases where y is equal to 1 and y is equal to 1, target number is 1, and then our output is 0.98. So the difference is very small. The difference between our target value and output value is very small. And also let's calculate the cross entropy. In this case, it is becoming small number. However, let's case in which we have a large difference between our target number and our output, then gradient should be large and we have to keep continuing the training process. In this case, cross entropy cost function becomes 13.288. It is large, small. For first meaning is that if there is a large difference between output and our target value, cross entropy output also is proportional to. If this is large, and this is large. If this is becoming small, this is small. So the very cost function is consistent with the difference of the output. Another meaning here is that the difference between target value and our output value is the small number, but cross entropy of our case A and case B is much larger, enlarged, so amplified. So cross entropy actually makes the difference makes a larger and larger. So it will help our optimization process very easily and very fast. So I would like to say that if we are using the cross entropy function, this training process, and by looking at this is very consistent. So cross correlation, cross entropy is really proportional to an amplification of the difference between target value and output value. So it is very consistent property and it is very fast. And I think it is a good cost function. Now, today we are talking about the cost function, which are very useful for fast, deep neural network training process. And one of the good candidates is, as I mentioned in this class, is the cross entropy function. So now I'm keep talking about the properties and mathematical descriptions and regressions process for this cross entropy function. Let me spend a little bit more about the meaning about this entropy. As I said before, this is a cross entropy cost function. Let's talk a little bit about the cross entropy cost function. This I is called information. Let's assume that you have a coin, and sometimes if you throw the coin, it has a probability of face up, and sometimes you have a probability of face down. The probability of face up is 1/2, and probability of face down is 1/2. So in this case, if we apply this information, entropy information, then I equal to is equal to 1. That means 1 bit. So when you are describing this information of coin flip and coin down, flip down, information you have is 1 bit is enough. Whether your coin is facing up or face down, 1 bit digital information is good enough information. However, let's assume you have a cube. You throw the cube, and there will be six different cases. So information will be so usually when we are using the entropy to describe the information, in this case we have only 2 cases, but in this case we have 6 different cases. So in terms of entropy, this is a higher entropy 2. This is a case of entropy 1. Entropy 2 is higher than entropy 1. So what does that mean is that if your system has a smaller entropy, that is good for classification. If your entropy is higher, it is very difficult to which one is your answer. But in this case of coin flip, we have only 2 cases, 0 or 1. At least you have 50% chance. So this case where entropy is smaller, your DNN output has more chance of higher accuracy classification. This is very brief understanding of entropy, which I can give you right now. Here, this is a kind of entropy function, and here is your target value. But anyhow, this y, log y means that minus log y is a kind of information and y dash is probability. If we this entropy small means that you have more classifications. You have more probability to reach a right answer. But however, if your entropy is very large, that is the case of Q, you have much more choices, uniform distributions. Let's assume that this is water. Let's you put on ink, then it will spread all over the water in a minute. However, if you this is the oil and you put ink there, because of let's assume this is water type ink, then it will not spread, it will explain, it will just stay there. So I would say this is the entropy 2, and if this is entropy 1, I would say this entropy, this is lower entropy, this is higher entropy. Mathematically, log y is high, this log y is small. And this is a case where it is good for classification. This is hard classification. Our class is not statistics class. Our class is more or like machine learning and reinforcement learning, but we cannot go very deeply into the meaning of entropy. But what I would say that if you have very good uniform, if you have very uniform distribution like this, where you put water ink on the top of water in a minute, or it will spread all over your water tank. And in this case, it's the very high entropy and uniform distribution. And it may not be a good solution for our machine learning purpose, because we want to have very clear, accurate classification. That is the property or our target or our goal of machine learning. Meanwhile, there is another case where if let's assume we have an oil, butter oil or whatever oil being used in the kitchen, then if you put small dot of water ink, it will just stay there. It will not spread. That is case where entropy is lower. This is very higher entropy. And in this case, where distinctive distribution, but here has more uniform distribution. And mathematically, I would say this is a case where minus log y has lower number, and here is the mathematically, I would say this minus log y has a higher number. And so I think this is the good candidate for our classification. So if we choose entropy as our cost function, smaller entropy means the very good optimization of our weight matrix and bias matrix. That is why we are using this cross entropy function and as a cost function of our deep neural network. Let me give you a little bit more examples, numerical example. The foreign student may not be accustomed to this game, but I would like to explain youth game. Youth game, it had we have 6 wooden sticks, 4 wooden sticks. We throw them. Each has a half of the probability. And cross entropy is, if I would like to calculate cross entropy, it has this shape. First term is coming from do, second term is actually coming from ge, 걸, 유, 모. So actually this term is actually coming from for only one stick is flipped. This is a case where so only one wooden stick is facing up, the others are facing down. You just throw the wood stick, and this is probability. This is the probability, and this actually entropy, and this is probability. If we can keep calculating all that, that is becoming 2.0306 bit. I would like to say if we can continue this for same as for cube, the number is smaller. My point is that entropy of U entropy of U game is smaller than entropy of Q. That means is that Q, when you are throwing cube, it is all the 6 spaces are uniform. So it has a little bit higher entropy number. However, in the case of 도개, 걸륜, 모 game, probability of do, probability of 개, probability of 걸, 윤, 모 are different. It is not, it's more likely in the cube case, it has all 6 are the same probability. But in the case of 윤, 도개, 도, 개, 걸, 윤, 모 has different distribution. You can imagine that probability of do are 4 to 16, ge is 6 over 16, 걸 is 4 divided by 16, 걸 is 1 over 16, mo is 1 over 16. So 1, 2, 3, 4, 5 cases are all different. However, in the case of cube game, if you throw the cube, all of them have same probability of 1 over 6. So if we calculate entropy of youth game and cube game, we found that youth game has smaller entropy number. Of course, we multiplied it with the probabilities. So lower cross entropy means that you have more distinctive distribution. If you have higher and higher entropy, you have more uniform distributions. But our case of supervised learning in deep neural network, we like more clear classifications. Your answer should be 99% to the right target, and others are just minimal. I think that is our target of DNN training process. With that concept in your mind, I would say that why we are choosing this entropy cluster function. second reason is that it is very consistent and because of derivation properties. And especially when it is near 0 or 1, it has very fast training and gradient is not vanishing. That is the basic properties of the entropy cost function. So today I have been talking about the entropy cost function and their properties. It is a little bit lengthy and broad class, but I think based on my experience, choice of activation function and cost function is very important part of your deep neural network design process. And in many cases, we are not, for the education purpose, we can use this mean square function. But in many cases, like CNN or DNN, we are using the cross correlation function. And next week, in the next class, I'm gonna also talk about a little bit about softmax and log likelihood activation function, but that is small part of the class. And I wanted to give details about this cross entropy function so that you will have more confidence on the use of the entropy cost function. Also, I briefly showed you the process of this regressions, how this B will affect this cost and how B will affect the difference between our target sigmoid and our output. And the optimization of B means that we have to make the change Y output function of your DNN network as closely matched to your target Y dash. And that is in cost function perspective, that is a process from 1, 2, 3, 4 in the cost function. This is the end of my class today. Thank you for your kind attention.